Hi, I'm Ann Moss, and this is my Physics 2211 Lab 5 on the falling slinky. So the purpose of this experiment is to analyze the motion of a falling slinky using video data and applying fundamental physics principles to model the slinky's behavior. The fundamental physics principles used were Newton's second law, which can be used to derive position and velocity update formulas. Newton's second law is force equals mass times acceleration, which we can transform into the momentum principle and then derive the position and velocity update formulas. Additionally, we have the gravitational and slinky force. The slinky force acts as the tension, and it is the opposite of the gravitational force. So the gravitational force equals negative mg, while the force of the slinky, or force of tension, equals mg. We also have the drag force, which is the resistive force offered by a fluid, such as air in this case, and the equation is seen below. And then we also have the center of mass motion, so the center of mass follows normal free fall. For this lab, the tracker app was used to observe the change in position of the slinky in the video, and then a computational model was then created to predict the motion of the slinky, and those two were compared. And then for the results preview, we have the bottom of the slinky remains mostly stationary as it's dropped. So for the tracker analysis, we had the system as the slinky and the surroundings as earth and wind. The mass was 0.21 kilograms and started at a height of 1.75 meters. The initial position in the x direction was negative 1.632 times 10 to the negative 3. In the y direction, it was 2.725 times 10 to the negative 4th, and in the z direction, 0. The initial velocity was also 0. And then before the release, the tension balances the weight, so the system is in equilibrium. And after release, the top loses tension first and causes collapse to propagate downward. I also forgot to mention we used a delta T of 0.01. The data from the tracker analysis can also be seen on the right side of the slide. We're primarily looking at the bottom graph, focusing on the y-axis, and it stays pretty consistent until it starts to dip around 5.5 seconds. So for the initial conditions in the computational model, we have the same ball mass, position, and velocity as mentioned in the previous slide, and delta T is still 0.01, and then we have gravity as 9.8 and J hat as 0.10. For the first timestamp in the loop, we use T equals 5.533. And then you can see we calculated force of gravity and the force of tension to calculate the total net force. And then the position and velocity update formulas were used to update the position and velocity. And then we changed the clock and plotted the curve. Now for the second loop, we updated the time to 8.133, and we calculated the force of gravity again, but then calculated the drag force this time, and then found the net force, and then we updated position and velocity again with the position and velocity update formulas, and then similarly the clock was changed and the curve was plotted. So the results of the observed and computed motion of the slinky turned out to be extremely similar. There's a slight differentiation of the two models around the 5.5 mark, but this is likely due to unaccounted for forces in the observed model video. So for possible sources of error, we have human error when using the tracker app, meaning not all points could have been accurately accounted for, and then also, like I said before, unaccounted for forces in the video used for the tracker data. Okay, and now we have our what if and what does it mean question. For the what if question, we have what if the slinky was dropped on the moon. The bottom would still remain momentarily at rest, but the delay would be longer and the fall slower because the moon's weaker gravitational force, which is 1.6 meters per second squared compared to Earth's 9.8 meters per second squared, reduces the net force in Newton's second law. Since gravity is smaller, the tension forces within the slinky also change more gradually, so it takes longer for the loss of the tension to propagate downwards. For the what does it mean question, we have why does the bottom of the slinky stay stationary? So the bottom of the slinky stays stationary because the upward tension initially balances gravity, and it doesn't start falling until the release of tension propagates down from the top.